In the figure 5.14, we see the IPv6 header with payload length 1448 bytes as expected. The next header field contains the value 44 0x2c we saw in table 5.5, indicating that a fragment header follows the IPv6 header. The fragment header indicates that following header is for ICMPv6, meaning there are no more extension headers. Also, the offset field is 181, meaning this fragment contains data at byte offset 1448 in the original datagram. We know it's not the last fragment because the more fragments field is set, displayed as yes by Wireshark. Figure 5.15 shows the final fragment of the initial ICMPv6 echo request datagram. Figure 5.15, the last fragment of the first ICMPv6 echo request datagram has an offset of 362 times 8 equal 2896 and payload length of 1072 bytes, 1064 bytes of the original datagram's payload, plus 8 bytes of the fragment header. The more fragments bit field being set to 0 indicates that this is the last fragment, and the original datagram's total payload length is 2896 plus 1064 equal 3960 bytes. 3956 bytes of ICMP data plus 8 bytes for the ICMPv6 header. See Chapter 8. In Figure 5.15, we see that the offset field has the value 362, but this is in 8-byte units, meaning that the byte offset relative to the original datagram is 362 times 8 equal 2896. The total length field has the value 1072, which includes 8 bytes for the fragment header. Wireshark computes the fragmentation pattern for us, indicating that the first and second fragments contain the first and second sets of 1448 bytes, and the final fragment contained 1064. All in all, the fragmentation process added 40 times 2 plus 8 times 3 equal 104 bytes to be carried by network layer. 2 additional IPv6 header plus an 8-byte fragment header for each fragment. If we add link layer overhead, the total comes to 104 plus 2 times 18 equal 140 bytes. Each new Ethernet frame includes a 14-byte header and a 4-byte CRC. IP forwarding. Conceptually, IP forwarding is simple, especially for a host. If the destination is directly connected to the host, like a point-to-point link, or on a shared network, like Ethernet, the IP datagram is sent directly to the destination. A router is not required or used. Otherwise, the host sends the datagram to a single router called the default router and lets the router deliver the datagram to its destination. This simple scheme handles most of configurations. In this section, we investigate the details of this simple situation and also how IP forwarding works when the situation is not as simple. We begin by noting that most hosts today can be configured to be routers as well as hosts, and many networks use an internet-connected PC to act as a router, and also a firewall as we discussed in Chapter 7. What differentiates a host from a router to IP is how IP datagrams are handled. A host never forwards datagrams. It does not originate, whereas routers do. In our general scheme, the IP protocol can receive a datagram either from another protocol on the same machine, TCP, UDP, etc., or from a network interface. The IP layer has some information in memory, usually called a routing table or forwarding table, which it searches each time it receives a datagram to send. When a datagram is received from a network interface, IP first checks if the destination IP address is one of its own IP addresses, i.e., one of the IP addresses associated with one of its network interfaces, or some other addresses for which it should receive traffic, such as an IP broadcast or multicast address. If so, the datagram is delivered to the protocol module specified by the protocol field in the IPv4 header or next header field in the IPv6 header. If the datagram is not destined for one of the IP addresses being used locally by the IP module, then first, if the IP layer was configured to act as a router, the datagram is forwarded, that is handled as an outgoing datagram as described in section 5.4.2. Or 2, the datagram is silently discarded. Under some circumstances, i.e. no route is known in case 1, an ICMP message may be sent back to the source indicating an error condition. Forwarding table. The IP protocol standards do not dictate the precise data required to be a forwarding table, as this choice is left up to the implementer of the IP protocol. Nevertheless, several key pieces of information are generally required to implement the forwarding table for IP, and we shall discuss this now. Each entry in the routing or forwarding table contains the following information fields, at least conceptually. Destination. This contains 32-bit field or 128-bit field for IPv6 used for matching the result of a masking operation. See the next bulleted item. The destination can be as simple as 0 for a default route covering all destinations, or as long as the full length of an IP address. In the case of a host route that describes only a single destination. Mask. This contains a 32-bit field, 128-bit field for IPv6 applied as a bitwise and masked to the destination IP address of a datagram being looked up in the forwarding table. The mask result is compared with the set of destinations in the forwarding table entries. Next hop. This contains the 32-bit IPv4 address or 128-bit IPv6 address of the next IP entity, router or host to which the datagram should be sent. The next hop entity is typically on a network shared with the system performing the forwarding lookup, meaning the two share the same network prefix. See Chapter 2. Interface. This contains an identifier used by the IP layer to reference the network interface that should be used to send the datagram to its next hop. For example, it could refer to a host 802.11 wireless interface, a wired Ethernet interface, or a PPP interface associated with a serial port. If the forwarding system is also the sender of the IP datagram, this field is used in selecting which source IP address to use on the outgoing datagram. See section 5.6.2.1. IP forwarding is performed on a hop-by-hop basis. As we can see from this forwarding table information, the routers and hosts do not contain the complete forwarding path to any destination, except, of course, those destinations that are directly connected to the host or router. IP forwarding provides the IP address of only the next hop entity to which the datagram is sent. It is assumed that the next hop is really closer to the destination that the forwarding system is, and that the next hop router is directly connected to, i.e., shares a common network prefix with the forwarding system. It is also generally assumed that no loops are constructed between the next hops so that a datagram does not circulate around the network until its TTL or hop limit expires. The job of ensuring correctness of the routing table is given to one or more routing protocols. Many different routing protocols are available to do this job, including RIP, OSPF, BGP, and IS-IS, to name a few. See for example DC05 for more detail on routing protocols. We have also discussed the BGP in the previous first videos regarding the connection to converge of our router. IP forwarding actions. When the IP layer in a host or router needs to send an IP datagram to a next hop, router, or host, it first examines the destination IP address D in the datagram. Using the value D, the following longest prefix match algorithm is executed on the forwarding table. First, search the table for entries for which the following property holds. D to M1 equal D1, where M1 is the value of the mask field associated with the forwarding entry E1 having index J and D1. Is the value of the destination field associated with E1. This means that the destination IP address D is bitwise and ED with the mask in each forwarding table entry, M1, and the result is compared against the destination in the same forwarding table entry D1. If the property holds, the entry E1 here is a match for the destination IP address. When a match happens, the algorithm notes the entry index J here and how many bits in the mask M1 were set to 1. The more bits set to 1, the better the match. Second, the best matching entry EK, i.e. the one with the largest number of 1 bits in its mask MK, is selected and its next hop field NK is used as the next hop IP address in forwarding the datagram. If no matches in the forwarding table are found, the datagram is undeliverable. If the undeliverable datagram was generated locally on this host, a host unreachable error is normally returned to the application that generated the datagram. On a router, an ICMP message is normally sent back to the host that sent the datagram. In some circumstances, more than one entry may match an equal number of 1 bits. This can happen, for example, when more than one default route is available, i.e. when attached to more than one ISP called multi-homing. The end system behavior in such cases is not set by standard and is instead specific to the operating system's protocol's implementation. A common behavior is for the system to simply choose the first match. More sophisticated systems may attempt to load balance or split traffic across the multiple routes. Studies suggest that multi-homing can be beneficial not only for large enterprises but also for residential uses. Examples. To get a solid understanding of how IP forwarding works both in the simple local environment, i.e. SIMLAN, and in the somewhat more complicated multi-hop global internet environment, we'll look at two cases. The first case, where all systems are using the same network prefix, is called direct delivery, and the other case is called indirect delivery. See figure 5.16. Direct delivery. First, consider a simple example. Our Windows XP host with IPv4 address S and MAC address S, which we will just call S, has an IP datagram to send to our Linux host. IPv address D, MAC address D, which we will call D. These systems are interconnected using a switch. Both hosts are on the same Ethernet. See inside front cover. Figure 5.16 top shows the delivery of the datagram. When the IP layer in S receives a datagram to send from one of the upper layers, such as TCP or UDP, it searches its forwarding table. We would expect the forwarding table on S to contain the information shown in Table 5.8. Figure 5.16 and Table 5.8. Direct delivery does not require the presence of a router. IP datagrams are encapsulated in a link layer frame that directly identifies the source and destination. Indirect delivery involves a router. Data is forwarded to the router using the router's link layer address as the destination link layer address. The router's IP address does not appear in the datagram unless the router itself is the source or destination, or when source routing is used. In Table 5.8, the destination IPv4 address D 10.0.0.9 matches both the first and second forwarding table entries because it matches the second entry better, 25 bits instead of none. The gateway or next hop address is 10.0.0.100. The address is thus the gateway portion of the entry contains the address of the sending host own network interface. No router is referenced, indicating that direct delivery is to be used to send the datagram. Table 5.8. The unicast IPv4 forwarding table at host S contains only two entries. Host S is configured with IPv4 address and subnet mask 10.0.0.100/25. Datagrams destined for addresses in the range 10.0.0.1 through 10.0.0.126 use the second forwarding table entry and are sent using direct delivery. All other datagrams use the first entry and given to router R with IPv4 address 10.0.0.1. The datagram is encapsulated in a lower layer frame destined for the target host D. If the lower layer address of the target host is unknown, the ARP protocol for IPv4, see Chapter 4, or neighbor solicitation for IPv6, see Chapter 8, operation may invoke at this point to determine the correct lower layer address, D. Once known, the destination address in the datagram is D's IPv4 address 10.0.0.0.9, and D is placed in the destination IP address field in the lower layer header. The switch delivers the frame D based solely on the link layer address D. It pays no attention to the IP addresses. Indirect delivery. Now consider another example. Our Windows host has an IP datagram to send to the host ftp.uu.net whose IPv4 address is 192.48.96.9. Figure 5.16 bottom shows the conceptual path of the datagram through four routers. First, the Windows machine searches its forwarding table but does not find a matching prefix on the local network. It uses its default route entry, which matches every destination but with no 1 bits at all. The default entry indicates that the appropriate next hop gateway is 10.0.0.1, thus A side of the router R1. This is a typical scenario for a home network. Recall that in the direct delivery case, the source and destination IP addresses correspond to those associated with the source and destination hosts. The same is true for the lower layer, Ethernet addresses. In indirect delivery, the IP addresses correspond to the source and destination host as before, but the lower layer addresses do not. Instead, the lower layer addresses determine which machines receive the frame containing the datagram on a per hop basis. In this example, the lower layer address needed is the Ethernet address of the next hop router's R1's A side interface. The lower layer address corresponding to IPv4 address 10.0.0.1. This is accomplished by ARP or a neighbor solicitation request if this example were using IPv6. On the networks interconnecting S and R1, once R1 responds with its A side lower layer address, S sends the datagram to R1. Delivery from S to R1 takes place based on processing only the lower layer headers, more specifically the lower layer destination address. Upon receipt of the datagram, R1 checks its forwarding table. The information in table 5.9 would be typical. Table 5.9, the forwarding table at R1 indicates that address translation should be performed for traffic. The router has a private address on one side, 10.0.0.1, and a public address on the other, 70.231.132.85. Address translation is used to make datagrams originating on the 10.0.0/25 network appear to the internet as though they had been sent from 70.231.132.85. When R1 receives the datagram, it realizes that datagram's destination IP address is not one of its own, so it forwards the datagram. Its forwarding table is searched and the default entry is used. The default entry in this case has a next hop within the ISP servicing the network, 70.231.159.254. This is R2's A-side interface. This address happens to be within SBC's DSL network, called by the somewhat cumbersome name ADSL 70.231.159.254.dsl.snfc21.sbcglobal.net. Because this router is in the global internet and the Windows machine source address is the private address 10.0.0.100, R1 performs network address translation NAT on the datagram to make it routable on the internet. The NAT operations results in the datagram having the new address 70.231.132.85, which corresponds to R1B's site interface. Networks that do not use private addressing, i.e. ISPs and larger enterprises, avoid the last step and the original source address remains unchanged. NAT is described in more detail in Chapter 7. When R2 inside the ISP receives the datagram, it goes through the same steps that local router R1 did, except for the NAT operation. If the datagram is not destined for one of its own IP addresses, the datagram is forwarded. In this case, the router usually has not only a default route but several others, depending on its connectivity to the rest of the internet and its own local policies. Note that IPv6 forwarding varies only slightly from conventional IPv4 forwarding. Aside from the larger addresses, IPv6 uses a slightly different mechanism, neighbor solicitation messages, to ascertain the lower layer addresses of its next hop. It is described in more detail in Chapter 8 as it is part of ICMPv6. In addition, IPv6 has both linked local addresses and global addresses. See Chapter 2. While global addresses behave like a regular IP addresses, linked local addresses can be used only on the same link. In addition, because all the linked local addresses share the same IPv6 prefix, FE80::/10, a multi-host may require user input to determine which interface to use when sending a datagram destined for a linked destination. To illustrate the use of linked local addresses, we start with our Windows XP machine, assuming IPv6 is enabled and operational. Ping 6 FE80::204:5AFF::FE9F::9E80, and then the prompt will return pinging FE80 etc. with 32 bytes of data. No route to next line, no route to destination. Then specify correct scope ID or use -s to specify source address, etc. Then ping 6 FE80::5AFF::FE9F::9E80 %6 pinging FE80 etc. %6. Next line from FE80 etc. with 32 bytes of total. Then reply from FE80 etc. bytes equal 32 time equal 1 ms. Reply etc. Then ping statistics for FE80. Next line, packets send equals to 4, receive equal to 4, lost equals to 0, 0% loss. Next line, approximate round trip times in milliseconds. minimum equal 1 ms, comma, maximum equal 1 ms, comma, average equal 1 ms. Here we see that failing to specify which interface to use for outbound link local results in an error. In Windows XP, we can specify either a scope ID or a source address. In this example, we specify the scope ID as an interface number using the %6 extension to the destination address. This informs the system to use interface number 6 as the correct interface when sending the ping traffic. To see the path to an IP destination, we can use the traceroute program called tracecert on Windows, which has a slightly different set of options, with the -n option to not convert IP addresses to names. In Linux, you type this in command line, traceroute -n ftp.uu.net. Next line, result of the prompt, traceroute to ftp.uu.net, argument 192.48.96.9, 30 hops max, 38 bytes packets. So as we can see, we have 17 lines here. This program lists each of the IP hops traversed while sending a series of datagrams to the destination ftp.uu.net. 192.48.96.9. The traceroute program uses a combination of UDP datagrams with increasing TTL over time and ICMP messages used to detect each hop when the UDP datagrams expire to accomplish its task. 3 UDP packets are sent at each TTL value, providing 3 round-trip measurements to each hop. Traditionally, traceroute has carried only IP information, but here we also see the following line. MPLS label equal 32307, COS equal to 5, TTL equal 1, S equal 0. This indicates that multi-protocol label switching MPLS is being used on the path, and the label ID is 32307. Class of service is 5, TTL is 1, and the message is not the bottom of the MPLS label stock, S equals 0, CRFC 4950. MPLS is a form of link layer network capable of carrying multiple network protocols. Its interaction with ICMP is described in RFC 4950, and its handling of IPv4 packets containing options is described in RFC 6178. Many network operators use it for traffic engineering purposes, controlling where network traffic flows through their networks. Discussion. In the examples we have just seen, there are a few key points that should be kept in mind regarding the operation of IP unicast forwarding. First, most of the hosts and routers in this example use a default route consisting of a single forwarding table entry of this form: mask 0, destination 0, next hop, some IP address. Indeed, most hosts and most routers at the edge of the internet can use a default route for everything other than destinations on local networks because there is only one interface available that provides connectivity to the rest of the internet. Second, the source and destination IP addresses in the datagram never change once in the regular internet. This is always the case unless either source routing is used or when other functions such as NAT, as in the example, are encountered along the data path. Forwarding decisions at the IP layer are based on the destination address. A different lower layer header is used on each link that uses addressing, and the lower layer destination address, if present, always contains the lower layer address of the next hop. Therefore, lower layer headers routinely change as the datagram is moved along each hop toward its destination. In our example, both Ethernet LANs encapsulated a link layer header containing the next hop's Ethernet address, but the DSL link did not. Lower layer addresses are normally obtained using ARP, see Chapter 4 for IPv4, and ICMP v6 neighbor discovery for IPv6, see Chapter 8.